computer audio. Start video. Ben, we have Ben Harris with us. Let's see who else we have. Oh, we have a good crowd. We have Darren, Ben, Brendan. We have two Bens. We have Ben Seaman, Ben Harris, Ashley, Brendan. We got a good crowd. Somebody out there unmute and say hi so I'll know I'm connected.
Hello.
Hello. Who is that?
Darren, sir.
Darren. Nice to hear from you, Darren. Looks like a beautiful day today.
Yes, sir. It was nice after all that rain.
Yeah. I planted some turnip seeds in my garden before that rain happened. That rain came along just right. So maybe I'll have some turnip greens in a month or so. Darren, do you eat turnip greens?
No, sir. I am.
You're not a turnip green kind of guy, I guess.
No, sir.
That's all right. Everybody's different. Well, let's see. We got a good crowd, and it's oh gosh, class starts in 2 minutes. Does anyone have a question for me?
Mr. Griffin?
Yes.
Six.
Talk into the microphone.
On the problem 3-6 on our course, so since we are guessing the value for the modulus of toughness, do you count the answer of 16,900 okay, or do you want the book answer?
Oh, well, let me see that one. It's 3-6, is it?
Yes.
Okay, now I did it, and I got 17 something. What did you get, Mohammed?
I got around about 17 too.
Say that again, please.
I got 16,900, so you can say like 17.
Well, okay, now let me write the units down. Now we're talking about this problem 3-6.
Mm-hmm.
And it's the modulus of toughness. And what I got might be different than what you got. I got 17.7 kip inches per cubic inch. Now, Mohammed, tell me what you got.
I got 16,900.
16,900
pound
inch
per inch cube.
Well, that's the same thing as what I got. You're fine. I will take anything from about, I don't know, 16 to 18, okay? Anything in there, don't worry about it. It's really hard to estimate that that area thing. Well, let's see, I need to adjust. Yeah, there we go. That's good. Yeah. So you're fine. Mohammed, you're just fine. I'm happy with what you got.
Okay, thank you.
Is there anybody else that has a comment or question there? Okay, well, let's see. Today's Thursday, and you have some homework, I believe, due tomorrow night. In fact, it was this one here. This one's due, Mohammed, that one's due tomorrow night, isn't it? Yeah.
sir.
That's due tomorrow night. Now you have
Yes.
another one. See what that is homework number 11. Yeah, that's homework number 11. That's just what I got. Don't worry about that if you got something different. See what that was is the modulus of toughness. That's the energy per volume that your specimen can take all the way up to fracture. That's what that is. Now, you also have homework number 12. See, this one's due Friday. But this one here is 325, and it's due Sunday. So you got some homework to do for me to keep me happy. And also, you need to start reading this chapter 4. We'll talk about it a little bit today. It's all about control volumes, mass flow rate. See, m dot, what that means is mass flowing into or out of a system per time. It's kilograms per second. And we're going to be studying that. We're going to enter the exciting world of control volumes. See, up till now, everything we've done has been control masses. But we're going to enter the world of control volume. Okay, well, good. Anybody else have a comment or question before we start the fun here? Okay, well, here, let's start the fun. I want to continue with our chapter 3 here to make sure we know how to do it. And let's do problem 333. I want to do problem 333. So I'm going to erase all this stuff. But you don't need me to write that. It's in the syllabus or the schedule. It's all right there. But we're going to do problem 333. Let me get rid of this stuff here so I can have some room. And we'll do 333. Let me see if I can find it here. Maybe, hey, I got lucky, I found it. The shear stress, shear strain diagram for an alloy, blah, blah, blah. Bolt is 0.25 inch diameter. Find the modulus of elasticity. Okay. Now, what they did was they plotted up the shear stress, shear strain curve. You see that tau right there, that Greek letter tau? That's shear stress. And this gamma, this is a Greek letter gamma. That's shear strain. And then here, they came up here. This is 0.004. And this is 50 KSI. And you know the equation, Hooke's law goes like this. See, maybe you're happier with this Hooke's law here. These are just both different versions of Hooke's law. This one's for shear stress and shear strain. This one's for normal stress and normal strain. They call this the modulus of elasticity, and they call that the modulus of rigidity. They have fancy names. But all this is just this slope here. It's just the slope. This G thing is equal to the slope. That's the rise over the run, which is 50 KSI divided by 0.004 nothings. See, strain has, it's dimensionless. Okay, I'm going to do that. I can't do that in my head. Let me do it on the calculator here. Okay, my calculator says it looks like 5 MSI. But somebody out there better double check me, make sure I did that right. I guess I did it right. Nobody said anything. Okay, now if you
I got a different number.
Okay, wait a minute. Let me do it. Let me do it again. Thank you for speaking up. I don't know what happened. I pushed the wrong button. Now who was that first spoke up?
Ashley.
Ashley, you just got a thank you point, Ashley. Good going. How about this? 12.5 MSI. How did I do that time, Ashley?
That's what I got.
Yay. Yay. See, I need you. Between you and me, we can do this stuff. Okay. Now let me read this and see what they wanted here. Bolt, determine. They want this thing. Well, you see, there's a relationship. I can't remember it, but it's in the book. Let me find it here. Here we go. There's a relationship that goes like this. This is the relationship between the modulus of rigidity and the modulus of elasticity. This little guy right here is the little Greek letter nu. And it's the Poisson ratio. And they gave it to us. They said it's 0.3. So let me write this stuff out. We got 12.5 MSI to 1 plus 0.3. We have an equation now with only one unknown, and I'm going to shut up and give you a minute, and I want you to find this capital E, the modulus of elasticity. Go for it. Well, I did that, and I got a value. I got 32.5 MSI. 32.5 MSI. Now, if that's right, I want to hear an uh-huh.
what I got.
Yeah.
Yep.
Yep. Yeah, we did great. So we did what they wanted. We found the modulus of elasticity. Now they want something else. They want the force P required to cause the material to yield. Well, it would be really helpful if you had a picture in your book of this. We're doing this problem 333. And it looks like it's going to yield right here. This is the, comes up here and yield. This is the yield strength shear stress. So here, I need a little room to operate here. I don't need any of this jazz here. We'll just get rid of it. See, they have a bolt. Let me draw that bolt. Artist's rendition of the bolt here. And they've got a piece of metal that has a force on that bolt going like that. And then another piece of metal with the force on the bolt going like that. And these forces they're calling it P for some reason. Trying to think of what they call that. My mind's a blank right now. It's a bearing stress. That bolt has bearing stress on it. See, there's a plate here. You really got to see this in your book to understand it, but they have a plate here, and then they have another plate here. And of course, this bolt comes down here and has some threads on it. And there's a nut right here. Somebody's tightened that nut up. And the external forces on the whole system are here, as in the book. So you've got this force here, you've got this force here. See, that's the external forces on your whole system, including the plates and the bolt and the nut that's screwed onto the bolt. But what we're interested in is the shear force and the shear stress on the bolt. So what we're going to do is we're going to section this bolt. And we're going to just forget this bottom part. We don't need it. And we're just going to look at the bolt. Never mind the plate. But if you just look at that bolt, the bolt has a bearing stress acting on it going this way, equal to P. And so therefore, it's got a shear stress, which we use, this book uses the symbol V for shear stress, which would equal P, of course. And they said the yield strength is 50 KSI. So you go, what you do is you go 50 KSI is equal to that shear force divided by the area. What they say, the diameter is 0.25. So you have to go pi over 4, 0.25 inches squared. And this V is equal to that P. So you could put the P in there if you wanted. They're equal. And we're going to solve for that for that force. Here goes. You do it. Why should I have all the fun? Here's an equation with only one unknown. I'll give you a minute. I want you to find that force that will cause the yielding. Well, I got an answer. I got an answer of 2454 pounds. Okay, let's see how we did. This was 333. Go to the back here and let's look up our answer and we'll see what they said. They said 333. They said that in the answer book that E is equal to 32.5. This is how they write it. That's what the book says for the answer. This is your book's answer. Hey, that's the same thing we got. You know what? That's the same thing. And then they said P equals 2.45 kip. Well, that's the same thing we got. That's 2,454. Yeah. Hey, we did great. We just did problem 333. Do you have any questions? Okay, well, let's do some more. I want to do 331 now. Okay, 331. Let me find some room here. Did anybody have a comment or question about the 333? Well, I guess you're okay. Okay, we're going to do 333 now. And we're still studying
$333 or $331?
yeah, thank you so much. I want to do 331. Guys, I'm getting mixed up. Did I tell you some nonsense about we're going to study control volumes? Did I say that? That's
At the
for
very
my
beginning of class.
that's for my thermo class.
Hey, still useful information.
Yeah. I don't know. I got my mind mixed up, and I was telling you something about thermodynamics. I do want you to read chapter 4, but chapter 4 is not about thermodynamics. I think we'll be in chapter 4 next time, won't we? Let me look and see here. I got mixed up. Okay, according to the schedule, today's the 25th, 24th. We don't meet again till next Tuesday. And yeah, we're in chapter 4. Yeah, chapter 4. So the part about reading chapter 4 is good. I do want you to read chapter 4. But it's not about thermodynamics. Somebody needed to speak up about that. Don't be shy, okay? Don't be shy. Just speak up. And now chapter 4 is all about tension and compression and axial loading. We've studied it a little bit already, but we're gonna know some new and exciting things about tension and compression when you have what they call axial loading. That's loading along a long straight member. So that's what we're going to do. But right now we're going to do 331. And right now we're studying shear stress and shear strain. Let me read this. The lap joint is connected together using blah, 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 blah. And, you know, this is similar to what we just studied, but this time they've got 2 plates. No, they have 3 plates. That one we just did only had 2 plates. This one's got 3. Okay, well, we can handle it. There's a plate here, yeah. And then there's another one here. Artist rendition here. And then there's a thicker plate here in the middle going like that. A little bit thicker there. And then you have a bolt. Here, we'll draw our bolt again here. A little artistic license there. And then see this bolt comes through here. Dash lines, okay? Dash lines. And then you have a nut. Yeah, that makes sense. You have a nut here. Yeah. And then the bolt comes through here like this, and it's got threads on it. Yeah, there you go. And somebody has got a force P here. And that means that this here and this here are half of a P. It's a P over 2, and this one's a P over 2. This is problem 331. And what we're going to do is we're going to section that bolt just like we did the other one. And if you section it right in here, you're going to have a shear force right in here. See, what I should do is I should erase this bottom part here. But can you see that you're going to have a shear force of P over 2? It'll be going to the left. Because see, we're going to erase all this bottom part. And you got P over 2 going to the left, and the shear, which is P over 2 going to the left, and then you got P going to the right. So the sum of the forces is 0. So what? Well, they said what P is. They gave us P. It's 150. Look here. It's 150 kips. So this shear force is 75 kips. Okay, great. 75 kips. Now the bolt has a diameter of 1.25 inches. So let's get the shear stress in the bolt. The shear stress in the bolt will be it'll be the shear force divided by the area, right? Which is 75 kips divided by pi over 4, 1.25 squared. Okay. I'm going to get the shear stress now acting in the bolt right there. Okay, well, let's see. You do it too. I'm going to call on somebody. I want to see if you can do this. Plug this in, and I'm going to call on one of my excellent students here in just a minute. I want you to find that shear stress. Let's call on somebody here. Let's call on this dang thing doesn't go all the way to the bottom. I got somebody here, but I don't know who it is. Yeah, there it is. It's Shane. Hey, Shane, unmute and say hi.
Hi.
Yeah. Hey, Shane, what'd you get for this, I got lost here. Yeah, for this shear stress, Shane, go ahead. What'd you get?
61.115.
That's what I got. I got 61.115. Now, Shane, what's the units on?
Okay. This is supposed to be unitless?
Shear stress has units, Shane. What are the units for stress?
Pounds?
No. Guess again.
Newtons?
No, not newtons. Because see, this is English, senor. Look at that inches there. We don't do newtons with inches, Shane. Come on now, you know this. The unit for stress is, try again, Shane.
PSI? It's not PSI.
Yeah, good going. PSI. See, you know it. Hey, have you ever noticed when somebody calls on you, your mind goes blank?
Every day.
Now you could write this as 61 point, I don't know, 12 KSI if you wanted to, just to give it a little pizzazz. But aren't you glad I called on you, Shane? Because, see, that's going to stick in your mind now. And you're going to know that the stress is in PSI, or you can write KSI, or what's the next one? The MSI? Yeah. That's good. But we're not done yet. That isn't just what we got to figure something else out. Let's read the problem here. If you tuned in late, you wondered, well, what's he doing now? We're doing problem 331. It's on page 116. And what do they want to know? Let me read this. They want the permanent shear strain in the bolt when the force is removed. You see this force here? Right now we have this amount of shear stress, but that's not what they want. They want the shear strain. Okay. They want this shear strain after the bolt is removed. Well, why don't we get the shear strain when the force is on there? And then we'll remove it. But first, let's find out what the strain is when the force is acting on the bolt. All right. Now to do that, we need this stress strain curve. Let me keep that 61 there that we got. And I hate to erase all this wonderful picture here, but we need the space for this stress strain diagram. Okay, stress strain diagram. Now this is a shear strain diagram. See, this here's that little Greek letter gamma, and this is a little Greek letter tau. And this comes up here like so. It goes, and then it goes. Now this value here is 50. And this value here is 75. Now those are KSI. This value here is 0.005. And this value here is 0.05. Now what we have is 61.12 KSI. Well, you know what? That's kind of in between 50 and 75, isn't it? It's kind of maybe right about here. You know what? We're right here. What we need to know to do this problem, we need to know what the strain is when the force is acting on it. Then we'll take the force off. But first, we've got to get this shear strain right here. We know it's between 0.005 and 0.05. We know what this value is right here. It's 61 point, it's 61.12. But how are we going to find this value here? We know it's between these two because 61 is between 50 and 75. Well, the way you do it is you make similar triangles. So let me do that in green here. I'm going to make a triangle right here. Before I do, though, I'm going to get the modulus of rigidity. That's just the slope in the elastic region. So it's 50 KSI over 0.005. All right, do that. I'll be quiet for about 45 seconds. I want you to find the modulus of rigidity for me. It's just the slope of the elastic region. Do it. And I'm going to call on one of my very best students here, Samuel. Samuel, unmute and say hi.
Hello.
Hello. Samuel, have you done this? Have you found this modulus of rigidity for us?
Yes, I got 10 MSI.
That's what I got. Good going. It's 10 MSI. That stands for 10 megapounds per square inch. That's what that stands for. Or you could say 10 million pounds. Mega is the same thing as a million, right? Good going, Samuel. Okay, now here we go. We're going to, I don't know if we needed to do that, but that was fun doing that. What we're going to do now is we're going to figure out what this strain is while the load's on there. And here's my plan. You see this little triangle right here? I'm putting it in green. And then I'm going to make another triangle. I think I'll put it in red. That's this one here. In geometry, they call those similar triangles. And you can set up a proportion. This little distance here is to that distance there. I don't know. Why don't we just call it X? But I know this little distance here. It's the difference between 50 and 6112. I can do that in my head. That's 11.12. See, if you subtract 50 from 6112, you get 11. I don't know if you can see that. Let me write it in black. Maybe black shows up better. It's 11.12 from there to there. So see, you set up this little ratio. 11, 12 is to, I'll just call it X right now, as that red line there, and I know what that is. That's the difference between 50 and 75. That's 25, isn't it? Is to this distance here. Well, I know what that is. That's 0.05 minus 0.005. I know what that is. That's 0.045, I think. Let me double check that. If you take 0.05 and you subtract 0.005, yeah, that's what you get. Hey, I can find what that little x is. Once I know what that little x is, I can find what this gamma is. All right, here goes. I'm going to solve this for x. I used similar triangles. Basically, I just said that the sine of this angle down here can be expressed like this or like this. These are both expressions of the sine of that angle down here. Okay, well, let's see what x is. Here goes. I hope somebody out there is following along with me. I'm getting 0.02. We can round that off, that's fine. And now, if you agree with that, I can get this strain here when the thing is loaded. I tell you what it'll be. It'll be that x plus the 0.005. Well, what's 0.005 plus 0.02? Well, it's 0.025, isn't it? Did I do that right? So now I know what this strain is. When you're loaded, the strain is 0.025. Does that make sense? Is that in between 0.005 and 0.05? Well, yeah, I think it is. I think 25 is between 5 and 50. Yeah, that works. We now know what the strain is with the load on, but we're going to take the load off. If you read the problem, it says, well, it says determine the permanent shear strain of the bolt when the load is removed. We're going to remove the load. Well, here goes. See, when you take the load off, the piece recovers. It doesn't go back to where it was in the beginning. It does this. It comes back here, parallel. See how I came back here? I tried to anyway. Parallel. They call it elastic recovery. When you take the load off, see, it's stretched. And when you take the load off, it shrinks back, but it doesn't shrink back all the way. And what they're asking us to find, that value of what it's got a name. It's called permanent strain. Read it. It says, determine the permanent shear strain. That's the permanent shear strain. Okay, well, we're going to try to find it. Now, here's the plan. We know we got a triangle here. Let me draw it for you. See this triangle? There's a triangle there. And we know the slope of that line. We know the rise over the run. Well, the rise over the run is the same rise over the run we had for this one. In other words, the 10 MSI that we got before. So what we're saying is the slope is equal to the rise over the run. See this here? The slope of that line is equal to the rise, which is this, over the run, which is that. Okay. Well, that rise, I tell you what it is. It's 61.12. Now the run, it's got a name. It's called the shear strain recovery. Here, I'll write it out for you. It's called the shear strain recovery. It's the shear strain recovery. Does that show up? Yeah, I think maybe you can read that. And see, we know what this slope is. It's 10 MSI. So let's put it in there. 10 MSI. Now this 6112 is in KSI. And this 10 is in MSI. Now I'm going to be quiet for a minute. And I want you to take your calculators. And I want you to find this shear strain recovery. You understand what that is? That's this distance here. That's the shear strain recovery. All right, go ahead. Well, I did that. Let me go to one of my excellent students here. Samuel, unmute, Samuel, and say hello.
Oh,
Hey, Samuel, did you solve this equation right here and get the shear strain recovery?
I got 0.00611.
That's what I got. Good going. Let me write that down here someplace. There's a little room over here. Maybe you can see this. Yeah, there's a little room over here. Now what we're talking about here is the shear strain recovery. And like my friend Samuel just said, it's 0.00612. Is that what you said, Samuel?
Yes, sir.
Yeah, good going. Okay, well, that's the recovery. Now, what they wanted, though, was the permanent strain. And maybe I could put that in a different color, like red, maybe. See, what they want is this here. That's the permanent strain. This thing recovers some, but it doesn't go back to where it started. You've got some permanent strain. And I tell you what that'll be. I need some room though. There's some room up here. We'll make us some room. Yeah, here we go. If you want the permanent shear strain, then what you want is the strain when you had the load, which was 0.025 nothings. And then we'll subtract the strain recovery, which Samuel got correct. It's 0.006112 nothings. And we're going to get the permanent strain. All right, go ahead and do that. So subtract that, and let's see what happens. I got the permanent strain is equal to 0.01, a bunch of 8s. We could just quit there. Nothings. That's the permanent strain. Now let's see how we did. This was problem 331. I go to the back and we're going to look up the answer here. This is 331. And we'll see what they said. 331. Here's what the answer book says. They said this gamma, they put a little p there for permanent, is 0.0189 radians. Now they said radians, but see, radians is dimensionless. It doesn't have any units like meters or pounds or anything. And I think we did pretty good. If you just rounded this off, I think there's another 8 after that, a whole bunch of 8s. Yeah, we did good. We got it. Yay, we got the permanent strain on problem 331. Okay. Is there any comment or question about that one? Let's see what we're going to do next here. Well, if you're happy with that, we'll do another one. Last chance to speak up about that one there. That was problem 331. And we got the right answer in the back of the book. Yay. Here's your last chance. Otherwise, I'm going to erase it. We're going to do something else. Okay. Say goodbye to 331, and we're going to do something else now. Now, the topic today is shear stress and shear strain. And I thought we could do fundamental problem 315. This is F 315. Okay, help me find it. Help me find F 315. Let's shop around here. F3. I found it. It's on page 114. You've got a 20 millimeter wide block firmly bonded to a rigid plate. Okay. They give you the modulus of rigidity. All right. Well, here, let me draw it for you. It's kind of a square block. It's square. One 150 millimeters by 150 millimeters. But now going back this way, it's only 20 millimeters. If you read it, it's just 20 millimeters wide, okay? And they have some metal plates on the top and the bottom. Now, I don't know what this block is made out of. Let me read it here. It's probably like a rubber or something. I don't know. It's got a smaller G than steel. Steel is 75, isn't it? If you go to the back of your book, yes, steel is 75. So we're talking something like might be aluminum. I was thinking maybe rubber, but no, it's kind of like aluminum maybe. We don't care. They never told us. But see, they put some plates here. Kind of hard for me to draw that, but I don't need to draw those plates. You understand? Then they're going to, I don't know, fix the bottom to the surface so it doesn't move, but the top's going to move. They're going to put forces on here. Do they tell you how big this force is? Let me read this. Force P is applied. It deforms the shape. Find it. No, we have to find that force. They tell us the modulus of rigidity is 26 gigapascal. Do not get mixed up between that G and that G. That G is called the modulus of rigidity. That G is called giga. We're not mixed up, are we? But now it's going to deform. So maybe I'll do that in, I don't know, maybe green. Let's do it in green. See, what happens is this block deforms and it does this. And so now, it's kind of a parallelogram type thing. Parallelepiped, maybe is that what they call that? And they said that this little distance here is 0.5 millimeters. See that little distance right there? It's 0.5 millimeters. Okay. Hey, I can get this angle here. Let's get that angle. You want to call it, I don't know, call it alpha maybe. That's a good name for it. Now, alpha is, in radians, it's 0.5 over 150. 0.5 millimeters over 150 millimeters. So in radians, it's 0.5 divided by 150. It's 0.00333, a whole bunch of threes, radians. I was telling you guys about this the other day. Now you could go with the tangent of alpha. I was showing you that. See, the tangent of alpha is the opposite over the adjacent. Isn't that how they do tangents? Opposite over adjacent. And guess what you'd get? You'd get 0.00333. Nothings. And so alpha, if you needed degrees, hit the arc tangent button, and I'm getting 0.19098 degrees. Now you can convert that to radians if you want by going pi over 180. And let's see what we get. Take those degrees, multiply by pi, divide by 180. And guess what you'll get? You'll get 0.0033, whole bunch of threes. There we go. I was telling you guys that for very small angles in the neighborhood of 1 or 2 degrees or less, and this is certainly less, this is about 1/5 of 1 degree. It's a very small angle. That the angle in radians is equal to the tangent of the angle. Not only that, it's equal to the sine of the angle. Let's take the sine of the angle and see what we get. Now the angle is 0.19098 degrees. Let's see what the sine of that is. 0.19098 degrees times the sine. Well, look here, I'm getting 0.00333, a whole bunch of threes. I told you this the other day, but I don't know if you caught it. Maybe I should write it. For angles, call it alpha, less than maybe 2 degrees, the angle is equal to the tangent of the angle, which is equal to the sine of the angle. But the catch is this has got to be in radians. The angle itself in radians is equal to the tangent of that angle. Now you can put that angle there in radians or degrees, it doesn't matter. But if you put it in radians, you need to be in radian mode. If you put it in degrees, you need to be in degree mode. Actually, at 2 degrees, you're off a tad, but not much. I forget what it is, something like less than 5% accuracy for sure. But for this one here, man, we're right on the money. Now, why did I do all that? Well, I'm trying to get the shear strain is what I'm trying to do. Now the shear strain, it turns out, is equal to this alpha. It's equal to that. Here, let me write that for you. What about this G? Do we need that for anything? Or is that from a previous problem? I got lost here. Does anybody know what that 26 is? Oh, that's given. It's in the problem. Okay. I need some room here. Here, let me make some room. Hope I'm not confusing you. Now the shear strain, this is our symbol for shear strain, right? It's a Greek letter gamma. It's equal to that angle alpha. It's equal to that. It's equal to 0.00, a whole bunch of threes. But now the way the book says to define shear strain, they say, and let's do it the way the book says to show you it comes out the same. They say take pi over 2 minus, I think they used a theta, where theta is this big angle here. Okay, let's try that. Now, what is that big angle? Wouldn't it be 90 minus this? See, we know that little angle. What is 90 minus 0.19098? I'm getting this big angle here is 89.80902. There you go. Almost 90 degrees. But see, we have to put that in radians. That's the catch. This has got to be in radians. So we're going to go pi over 2 minus this angle in radians. Okay, let me convert that to radians. Hang on. See, that's in degrees. So what you have to do is you have to multiply by pi, divide by 180. And what I'm getting is 1.56746 radians. So we're going to subtract 1.56746 radians. Okay, do that with me and we'll have our shear strain. Here goes. Subtract all that. Let's see what happens. Well, boy, Juve, you know what you get? You get 0.00333, a whole bunch of threes, don't you? So you can use this equation here, or you can use this equation here. You get the same answer. But we're not done yet. They wanted us to do something else here. Now let me read this. Determine the, we got to find this force P. We don't know what that force P is. Determine the magnitude of P. The block's material, blah, blah, blah. Well, now, how are we going to do that? Might need a little room here. Let's see. How about, we don't need that. You guys, you don't need any of that. There's some room. I just made us some room here. They want us to find this P. Well, how does it work? Shear strain is equal to the force divided by, and that's the force, divided by the area over which it operates. And that force and that area have to be parallel. Wait, well, see, there's an area right here. See it? That area is parallel to that force. And that area is, let me think now, it's 0.150 meters times 0.020 meters. See, that's that area. That's the force that's being applied to that area, and we can get the shear strain. Now here's the plan. That's not shear strain, it's shear stress. But see, that shear stress is equal to G, which is 26 gigapascal, times the shear strain, which we know. Let me circle that. The shear strain, we found it two different ways. It's 0.00333. We found it using the book formula. We found it using this very simple equation here. Okay, look here, guys. Here's an equation. Shear stress is equal to that P over the area, which is equal to 26 gigapascals times gamma, which we know. It's sitting right here. I'm going to shut up for a minute, and I want you to find that force P. Okay, go. I wonder if anybody's got that. Let me look and see here. Nicholas, unmute and say hi, please.
Hey.
Yeah. Hey, Nicholas, have you plugged this wonderful equation in and solved for P?
Yeah,
what?
259.74.
Yeah. Let me write that here someplace. Nicholas says P is equal to 259 point what, Nicholas?
74.
Yeah. Good going. Now what are the units?
I think it's Newton meters.
You're
No,
close.
it's Pascal meter squared, but I don't know how.
Okay, now a Pascal is a Newton per square meter. And if you multiply by square meters, what should you get? Newtons per, see, that's what a Pascal is. A Pascal is a Newton per square meter. Isn't that what you have here? Don't you have Newtons per square meter?
Yeah.
Yeah. Now, where'd the square meters come from? I'm getting lost here, Nicholas. I was doing great here. Well, you got Pascals on both sides. See, this is going to be Pascals, and that's going to be Pascals. That's a nothing there. Anyway, what I need to know, Nicholas, is I like your number here, but I need to know what the units are. What are the units on this 259.74?
I don't know. I don't know.
That's an honest answer. I like honest answers. Well, no, I see what you're doing, Nicholas. You got square meters here, and you have Pascals here, and nothing's here. And so what you have is Newtons per square meter times square meters. Nicholas,
So Newtons, right?
what do you get when you take Newtons per square meter times square meter?
Newtons.
You get newtons. Did you just say newtons?
I think so.
Yeah. Now newtons is good. The only thing is, this is going to be kilonewtons. Because really what you get in my calculator is 259.74 times 10 to the third. Is that what you got? See, that giga is 10 to the ninth, right?
Oh, yeah, I did make it. Sorry.
Did you make it 10 to the sixth?
Yeah.
Ah, that's not right. Giga is 10 to the ninth. Now, if you'll do that, you're going to come out with 259 kilonewtons. Now, let's see how we did. This was F315. Go to the back and help me snoop around. And 315 says, now the book says, you got lost, 260 kilonewtons. Now we got 259.7. They just rounded off. I'm pretty happy with that. I think we did pretty good on that. Well, we have a few minutes left, but I don't think I got time enough to do a whole lot in the time we have left. I think we've had enough fun for one day. Here's your chance to ask me anything. Go ahead, ask. Okay, nobody said anything. We're going to sign off here. We're going to say goodbye till Tuesday at 9:30, right? Yeah. Okay, guys. I'm going to see you Tuesday at 9:30. Enjoy your homework. Read that chapter 4 and say goodbye. Goodbye.
Yes,
Thank you
bye.
very much.
Yeah. Bye-bye.
Bye.
Bye.
Bye.